Okay, so now we're going to talk about surface integrals. So we're going to try to calculate the area of a surface. And so this is best done through just an example. Okay, so let's say we tried to do the surface integral. Okay, all right, so we have an f of x, y, z, and let's say x minus y divided by the square root of 2z plus 1. Okay, it's going to be ds. Okay, now we're going to have to define r. Okay, so where s, the surface that we're talking about, the surface integral that we're going to integrate, is represented by r of uv, which is going to be u plus vi plus u minus vj, and then plus u squared plus v squared k. All right, so we're given this f of x, y, z, a function of x, y, and z, and we have a surface that is defined by this r, u, and v. And it's defined on a domain, so our d is just going to be that 0 is going to be less than or equal to u, which is going to be less than or equal to 1. And the 0 is going to be less than or equal to v, which is going to be less than or equal to 2. Okay, so just the square. Okay, now for this representation of a surface integral, what is the first thing that we're going to have to do? We're going to have to do RU cross RB. Okay, and then we're going to have to find the magnitude of RU cross RB. So that's the first step of this problem. So the first thing to do is to figure out, well, what is r sub u and r sub b? These are partial derivatives of r with respect to u and the partial derivatives of r with respect to b. So r sub u, okay. Now, if I take the partial derivative of this component with respect to u, there's only one u, okay? So the derivative of u would just be 1, so this would be I. And the partial derivative of this guy with respect to u, well, that's just that u right there, plus j. And now the partial derivative with respect to u of this component right here is going to be plus 2uk, okay? Now, we have to consider what is r sub v. Okay, so now the partial derivative with respect to v, well, we don't care about that u, so that just goes to 0. And the partial derivative of b with respect to v is 1. So that's I minus j plus 2v times k. Now we have to do the cross product of these components. Okay? So RU cross RV. That's going to be the determinant of a matrix. That's I. That's K. This would be 1, 1, 2, U. And 1, -1, 2, V. Okay, so now if I do RU cross RV, I have to take the determinant of this matrix. So this is going to be I. Okay, so if I use this component right here, that's going to be 2V plus 2U. Right. And then minus J. Okay, so remember, when you do the middle component, it's going to be this one, this one, this one, this one. So that's going to be 2V minus 2U. And then plus K. Well, now we're looking at this section right here, so that would be, well, -1 minus 1. Okay, so let's simplify this up a little bit. So that's going to be I times 2V plus 2U plus J times 2U minus 2V. Well, and then let's just say K times -2. Okay, but let everybody write that down for a second. But we're going to have to figure out the magnitude of this thing, because it's going to be the magnitude multiplied by that F of R of UV. Okay, so we figured out what RU cross RV is. So the magnitude of RU cross RV is going to be the square root. Let's take all of our components and add them together. So that's going to be 2V plus 2U now squared plus, what was it? 2U minus 2V squared, and then plus a -2 squared. Okay, now every one of these components has a 2 squared in it. So the square root of 2 squared, you can just pull out a 2 from it. And so let's just pull a 2 out of everybody. So that's going to be V plus U squared, U minus V squared, and plus 1. Do a little bit of algebra. That's going to be V squared plus 2 UV plus U squared plus u squared minus 2uv plus v squared plus 1. Okay, we can do a little bit of cancellation right there. I can combine this guy and this guy and this guy and this guy. And so that's going to equal 2 times the square root of 2v squared plus 2u squared plus 1. Okay, so now we have the magnitude of RU cross RV. Okay, so that's the first thing that we got to do. We're looking for that guy. And so we found that component right there. Okay. So we found the magnitude of RU cross RV. So of x minus y square root of 2z plus 1 ds, which is going to equal double integral on the domain. Okay, so we're going to plug our x's and y's and z's into this thing. And so the x was u plus v, and then minus y would be u minus v divided by the square root of 2, and then our z was u squared plus v squared plus 1, and then multiplied by our RU cross RV, the magnitude of this one. And so that's going to be 2 root, I'll write this like this. So 2v squared plus 2u squared plus 1, and I ran out of room. Let's put that dA right there. Okay, and now what's the problem is that you can see that the cross product of the RU cross RV, it cancels out with the bottom. And we also have the u minus u, that's going to cancel out. And so what does this basically come down to is I'm going to have a v and I'm going to have a negative v. I mean, well, negative of a negative, and they end up canceling each other out. So that becomes 2v. And then we have another 2 right here. So this whole thing ends up just becoming the integral from 0 to 1 of 4v du dv. All right. Now, if I integrate 4v with respect to u, that just becomes 4vu evaluated at 0 and 1. And so if I plug 1 into this thing, that's just 4v. And so that becomes the integral from 0 to 2 of, well, just 4v with respect to v. And so that becomes 4. Now v squared divided by 2 evaluated at 0 and 2. And that becomes 4 times 2 squared divided by 2. All right, now 2 squared divided by 2 is 2. And that becomes 2 times 4, which is 8. And so that's the basics on becoming, if you have a parameterization of a surface, and in this case, it's just a square, as r is a function of u and v, that's how you would do the integral. So the next video will be, well, what if it's a vector space or something different?